Hello and welcome to this video on residuals using linear regression. First, we'll talk about what a residual is. It is basically the difference between what your actual data is. So you have a scatter plot with x, y, comma, y points, where your x is your input and y is your output. The residual itself is basically how different your actual outputs are from the outputs that you would be given by your regression equation. So you'd be plotting basically your original x value and then first plotting, well, what is our predicted y value based on a regression equation? The residual itself is, well, how different was your original y value to the y value you get from your regression equation? And it's going to be a positive or negative value because your original observation output, your y, is going to be a certain amount above or below what your regression equation would tell you about that same output. This is also known as least squares regression. There's a formula associated with that you would learn more in depth about in a traditional statistics class, which you may or may not take in your future. So we want to use these generally to see if a linear model is a good fit for data, and we can look at actually plotting the residual points, which is basically x comma the difference we mentioned on our last slide. And if there is sort of a pattern around your residual plots, well, then it's probably going to be a nonlinear pattern, a nonlinear model, like a quadratic curve of best fit or cubic or exponential or any other type of function that is out there. If there is no pattern at all, if your points are kind of above, kind of scattered around, then that generally means that you have a linear model instead. And to demonstrate what I mean by that, the picture on the left, that is for a linear model. And you can see that it's kind of around the x-axis. So these points are the residuals. So you have this first point where my cursor is, that point is a little above 0. So the difference between your original output and your regression output was a small positive number. So you have that same input, and then the output is that difference. So you have different amounts of difference between your original and your predicted one with your regression equation. The middle one, well, we have a U-shaped pattern, so nonlinear would be appropriate. If you an upside down U pattern, then it also means nonlinear. So if you have just scattered residuals, that definitely always means linear. So an example of doing this, we have 5 points, and you can see the 5 points listed up at the top here, and we made a scatter plot where basically just A and B are input and output. And you want to see if you make a you do linear regression, but you're not sure if it's going to be the best choice or not. And we have a regression equation already, 0.7x plus 0.7. So you would basically have your line that you would then plot using this linear equation right here. And that's what we see in this right here. So this blue line is that linear equation, 0.7x plus 0.7. So we have the original scatter plot points in purple, as you can see here on screen. Our regression points are basically taking those inputs and doing, for instance, in this first point, you would do 0.7 times 1 plus 0.7 would equal 1.4. That is just plugging a 1 into this equation right here. 1 times 0.7 plus 0.7 equals 1.4. So our predicted value for this first point is 1.4. And we do that for all these other regression points using the original inputs, plugging them into our regression equation. So these red lines are basically the residual parts. So for instance, in this first one, 2 compared to 1.4, our original point is 0.6 larger than the regression point. And then our second point is 1.1 smaller, and then we have 4.5 smaller, or not 4.5, it's 0.7 smaller, and so on. And those differences, these red differences, the difference between these two y values in each of these points are the residuals. How different is your original, the scatter plot, from your predicted, the regression points? And when you do that subtraction, you basically take your original y minus your predicted y. As you can see, if we go back a couple slides, you're doing your observed, your original minus your prediction. So basically, scatter plot minus regression. And then we do, so you have a scatter plot minus regression, you get 0.6. So this point right here is 1 comma 0.6. You can see that right here. So you can see basically it's just plotting how far are you from your line of best fit. So you can think of the x-axis right here on this calculator picture as being the line of best fit, and these points are how far the original basically was from our line of best fit. And because this doesn't seem to have a pattern, any kind of U shape, whether upside down or right side up, we can confirm that a linear model would be a pretty good fit for this data. So we're now going to try to kind of walk through this step by step using Desmos and see how that goes. So we want to make a table out of this data, temperature versus the revenue at this lemonade stand. So it makes sense that kind of looking at the data itself, the hotter it is, it seems like those are the warmer, the more revenue they're making from lemonade. And we're going to see if we can use a linear model for this. So we have our table and we have all our points plotted in Desmos here. So we want to first find our line of best fit. So using Desmos, we can do this really easily. Y, and then we can use our subscript 1. You can also use your keyboard button for that. And then we're going to shift, and then the button next to 1, the tilde, little squiggly line you can find on your keyboard. And then A, X sub 1 plus B. And we have a linear function for this. So we're going to kind of type in our linear function here. Y equals 1.22082 x minus 62.1685. So we have that now plotted on our graph here in Desmos. So we can get rid of our regression, and we basically just have our table here. So what we're basically going to do is make a table that kind of uses these x values using Desmos and basically have them plug all of these x values into our equation here. So that's what we're going to do next. So we're going to insert a table. Actually, we can scratch that and just hit that icon there and convert this into a table. So we're just going to type in our x values from our original 70.5 and 90.2, 75.2, and then 87.4, and then 93.6, and then 68.1. All right, so now let's adjust our color here. So we want our line to be dotted. We want to maybe just get rid of our line. And we basically, if we, so we have our regression points are all the purple parts here. So we have all of that happening here. And can we just call this? Okay. Well, we basically are now going to we can compare these numbers. So for instance, we could do 44 minus 38.9, and that would kind of be our residuals there. And we could kind of build another table with these numbers if we wanted to, instead of using our table feature in Desmos. But we could use it to kind of just save time here. So now, in order to kind of wrap this up, if we look back at our PowerPoint, we had our predicted value, and so we're now going to do our residuals, our residual values. So we basically would just be doing 44 minus 38.9, 23 minus 23.89, 46 minus 47.9. And so we can kind of try just some of those out. So if we we can add another table here. So for instance, 82.8, and then we're going to do 44 minus 38.915. And we're going to need to zoom out a little bit here so we can see that is our first residual point there. So you can see that's our x-axis. And we could do kind of these, maybe one other point here. So we have 70.5 is our second x. We did 23 minus our second row, so 23 minus 23.899. So we can see that as our second residual point. And this would kind of continue onwards as you go. And we can look at a finished product here in 1 second. Okay, we are back and we are looking at our table up here. We've added in residuals as this kind of E sub 1 column right here, where all those blue points are 82.8, 5.08, and we can kind of zoom in here. So you can see how they're kind of going up and down, no real pattern here. So it seems like we have a pretty good linear model for residuals in this particular example. So it seems like for temperature versus revenue, the temperature, that would be a good linear pattern that we're using here in regression. And that essentially is what residuals are. And Desmos allows us to find these residuals and make decisions on how good of a model that we are looking at. And that wraps up our notes on residuals for this video. Thank you for watching.